So in this section in 3.1, what we're looking at is what's called a quadratic function. A quadratic function, by the definition's actually here. It's just a function in this form. So a function f of x is a quadratic function if it's equal to a polynomial of degree 2. That's what a quadratic function is. Degree 2, again, that's the highest exponent of x, okay? Which here is 2, of course. The a, b, and c, those are constants. The a has to be non-zero, which really does make sense because if ax squared was not there, we would just have b times x plus c, but we've seen that function already. The graph is just a line. So now we have quadratic functions, and actually here's an example. We actually have dealt with these before. We've dealt with the function f of x equals x squared. In fact, we have even graphed it. The graph, let me just scroll this up. The graph looks like this. Okay? This is what the graph looks like. And in fact, the graph of not just this quadratic function, but any quadratic function is called a parabola. This is what the graph, again, looks like. Again, you can even see from the graph, actually, that the domain is all real numbers. In other words, let me scroll down a bit. You could take any number you want for x and plug it in, and you'll get a reasonable output. So in other words, the domain is all real numbers. Now, it turns out, as you see over as I wrote over here, that the graph of a quadratic function will actually depend on what a, b, and c are. In particular, if your a is positive, okay, as I have over here, the graph is going to open upward, just like the graph we saw on the previous screen. So if your a, let me draw it here, is positive, the graph has to do something like this. And it actually does keep on going. So just to indicate that, let me draw arrows here. So the graph does keep on going. And it's opening upward, in other words. You could have the case when a is negative. In particular, in this graph here, we have y equals negative x squared. And you can see that this graph is actually opening downward. Okay? This graph is opening downward. Okay? The domain is the same, but because it's opening downward, you could probably guess that the range is going to be different. Okay? The range is going to be different. So that's what we actually have here. Okay? I mean, the actual range for a quadratic function in general will depend on a, b, and c, but you can see, though, how that if a is negative, the graph is going to open downward. So just to be complete, let me just write this. Let me do this. We have a negative. Then the graph is going to open downward like this. Okay? And that's what we have below, because in that case here, we have a equals negative 1. Okay? I mean, the domain is the same, but again, the range will vary. Okay, now, if you go back to these graphs, let me draw some of those again. If you draw a parabola, you can see from the graph, so again, this is when a is positive. You can see from here, and in the case when a is negative, there is a point where the graph turns around. So there is a point where the graph makes a U-turn, so to say. Okay? And that point is actually very important. It's what we call the vertex of a parabola. So let me just make these graphs a little bit bigger. I know I'm drawing them a lot, but it is important. So when a is positive, remember, a cannot be 0, so a being positive or negative are the only cases then for a. But here, what we have then is the vertex. And also, there actually is a vertical line through the vertex that the graph is symmetric about. In other words, if you were to imagine taking this graph and folding it, almost like a book or a page, I guess, if you want, along this dashed vertical line, both halves of the graph would overlap each other. They would match up. maybe not so much from the graph I drew, but if you went back to the graph of y equals x squared or negative x squared, you would see that that does happen. Let me go back to y equals x squared. In fact, if you were to take this graph, it turns out here the vertex is down here, but if you were to take this graph and imagine folding it over the y-axis, both halves of the graph here, they would line up with each other. They would line up with each other. In negative x squared, the vertex you can see is also the origin. That's where the graph turns around. The axis of symmetry, again, it's the vertical line through the vertex. So again, here, it's the y-axis. But you can imagine taking the graph and folding it along the y-axis. Both halves of the graph would match up. So again, the vertical line, I drew it as a dashed line here, but that's okay. The vertical line that goes through the vertex, we call that the axis of symmetry. So we have vertex of the parabola and axis of symmetry. And again, this is when, what I'm drawing at the moment, this is when A happens to be a negative number. Okay? I mean, the exact, how do I say this? The way the graph will look like exactly in the Cartesian plane, you have to consider what B and C are. But if A is positive or negative, the graph's going to look something like this. So up here, this is what I was saying before about folding the graph in half, about the axis of symmetry. Now, it turns out there's actually another way to write out a quadratic function. We had one way earlier. Remember, that looked like this. Like so. Okay. All right. So again, you had A, B, and C there. But it actually turns out through a process of completing the square, you can actually write this, the quadratic function, in this form down here for some h and k. You can actually go, in other words, from this form to this form, and that's through the process of completing the square. And this form over here, which has the h and k, we call that the standard form of the quadratic function. Of course, you can go from the standard form back to this. You just basically foil x minus h squared, foil it out. Now you might be thinking, well, why would we even care about the standard form here? Well, it turns out if you have the standard form, you can easily get the vertex of the parabola. Namely, it turns out the point hk, as you can see down here, that is the vertex of the parabola. Again, that's where the graph turns around, so to say. But what's nice is also, they actually, I think, prove it in the book, you actually can get h and k in terms of a and b. It actually does turn out, let me just put it in a box here, but h does turn out to be negative b divided by 2 times a, and k, of course, is just f of h. Keep in mind, a is not 0, so this does actually make sense. So sort of like a summary, what we have here, if we have, this is actually what I'm going to emphasize for time consideration, if f of x turns out to be this, then as before, we have the domain, which is everything. The vertex turns out to be this here. Okay? Again, this is because we had the standard form. We know what h is in terms of a and b. hk, remember, is the vertex. And it turns out, actually, that h is equal to this. And this is just f of h. So in other words, this is the vertex. The axis of symmetry, again, that's the vertical line through the vertex. And that turns out to have this equation as well. For the y-intercept, that's actually pretty easy to get. I mean, basically what you do is calculate f of 0, and the y-intercept turns out to be then this point. You know, that's the point where the graph crosses the y-axis. So it turns out to be this. Okay. And now for the x-intercepts, well, in this case, you need to solve this equation. Now for the x-intercept, you have to solve that equation. Okay? And now, of course, we had different ways of doing that. I mean, there's more than two ways, but we saw only two. You could try factoring, or, of course, the quadratic formula. And then the x-intercepts, again, you're going to have points. Those are the points where the graph crosses the x-axis. Okay? Also, notice, again, even I indicated it before, but I didn't mention the range here. You actually could get the range from the vertex. You would have to know if A is positive or negative. Really, it's just best to get the graph, though, because then you can see it more visually.